So we discussed the frequency shift keying, and by definition, frequency shift keying is a form of digital modulation technique in which the frequency of the analog signal is varied to represent the input data, and such that as per this diagram, as per this figure, we have the input data as this one. Therefore, we have a series or sequence of zeros and ones, which are represented by unipolar non-return to zero signal, and we have discussed that in our previous lecture. This is our carrier signal with constant frequency of FC, but then we have we normally say that the binary data sequence is the modulating signal, or which is also the same as the message signal. So the message signal modulates the carrier. So that is important that we know what modulates the other. So the carrier has a constant frequency. It is modulated or it is varied. Actually, the word here is the modulation means varied. So we are varying the frequency of the carrier. Sometimes it goes slow, like we can see here. When we have a 0, there is a lower frequency being transmitted as F2, and when there is a higher frequency, when there is a 1 being transmitted, we have a higher frequency than the carrier frequency. So we normally say that the FC is offset to be by some value, such that at the end of the day we are going to be having F1 being equals to FC minus frequency offset delta F, or plus, and then F2 being the one that is lower, is equals to FC minus delta F, where delta F is the offset frequency. So now discussing, just going through these notes, we say that the peak amplitude and the phase remain constant, whereas the frequency changes in accordance with the levels of the digital data, as we have just illustrated. And mathematically, we can represent the BFSK signal as being equivalent of two signals, one that represents the 1 and another one that represents the binary 0. We say that the VC is the maximum amplitude of the carrier, and of course this is the VC, so it remains constant through the entire period of transmission or modulation, whereas the F1 and F2 are typically offset frequencies from the carrier frequency, and they are normally different of each other, or they are separated from each other by opposite values. So either we say F1 is more than FC by a certain value, which is opposite. So on this one goes the plus, and the other one goes to the negative. So that is what we mean here, but when we say that there are offset frequencies from the carrier frequency that are equal but opposite. So they are normally offset from the central frequency, which is FC. And of course, this figure shows the time domain waveform for the input digital data, as we have illustrated. The sinusoidal carrier signal, which is this one, and then the output BFSK signal, or binary phase shift frequency shift keying signal, as we have illustrated. It is quite clear that the lower frequency represents the binary 0, and the higher frequency, F1, represents the binary 1. So there are some observations that we can make from this, that when the input data changes from binary logic 0 to logic 1 and vice versa, the BFSK output shifts from F1 to F2, and we have seen that when we are transmitting a 1, we are shifting to F2 when we want to transmit as 0. The time duration of 1 bit is the same as the symbol bit duration. We are saying here that the symbol is the same as 1 bit, is the same as the bit. So one symbol is equivalent to 1 bit, and therefore the symbol rate or the bit rate and the baud rate are going to be the same.